Good morning. Let's continue on timing table. So we need to determine the outputs y1, y2, y3 for the following timing diagram. So the first step, you need to look at the circuits and determine, do we have flip-flops or latches, which type of flip-flops or which type of latch that we do. The first one is this one, flip-flop or latch? This is latch, because there's no triangle shape on the gates. So this is latch. The second one, this is JK flip-flop. Is this rising edge or falling edge? Or positive edge? It's positive edge, right? Because there's no bubble at the clock cycle. So it is JK flip-flop. The first one was the latch, this one JK flip-flop with positive edge or rising edge. The last one, it's flip-flop, T flip-flop, and it is falling edge. Why? Because there is a bubble. So it is falling edge. Now, we already have the clock already been given. X is given as well. We need to determine y1, y2, and y3. So the latch, the first one which is associated with the latch, is sensitive with the states. So is it on or off? It's not related to rising edge or falling edge. So let's draw the guidelines for the terminals. I'm drawing the guidelines because during the on period, y1 will change. During the off, will be hold. That's for the latch. While for the flip-flops, each one is depending on the application, if it is rising edge or falling edge. And let's assume here the initial conditions are zeros. So I'm going to write it here. Assume initial conditions zeros as zeros. So I'm going to start first with y1, which is associated with the latch. Y1, which is case sensitive. So here, again, the initial conditions are zeros. So here the initial condition is 0 for these parts. Then the on time, which is when the clock will be on, which will copy what's x, because d or the function d equal x or y1 equal x during the clock on. So we will copy what's the waveform of x, which is here, it is 0. Then after that, the next updates will happen when it will be on again. The next updates when it will be on, back on. So it will be on again here. Here's the next updates. So at this cycle. So the updates here. So here, since it is 1, it will be 1. Then in this area it will hold. The next update happen here, so it will back to 0. Here is back to 0. Then we will copy during the waveform. Then it will hold. Then on the next updates here, it will back to 0. then hold, next update, it will hold, then hold, copy during this time. We will copy what's happening with X, then it will hold, the next update here, it will hold that one, then here it will keep holding until the next update here, it will back to 0, then hold. Okay, does this make sense? This is the D latch. Basically, during the off times or during when the clock is zeros, like when the clock are zeros, it will hold. Look at the arrows when the clock are ones, you will copy the waveform of D. Okay? So this is for the first one. Now the second one, JK flip-flop. So in JK flip-flop, you need to look to have some observations at the JK. Let me write it in green color. Here's JK. In JK flip-flop, J is related to Y. It's not related to X. So you will no longer look at X, the first observation. The second observation, K is 1. Okay, so what's the points? In JK flip-flop, JK flip-flop, the function, we can call it Y2, is equal to J Q bar plus K bar Q. Okay? Now let's substitute the values. J is equal to Y1. Q bar plus K bar. K is 1. 1 bar Q. 1 bar is 0. Therefore, the term will no longer be valid. So Y2 will be Y Q1 bar. Okay? So how can we use this in the waveform? We can say if Y1 equals 0, therefore Y2 bar, Y2 will be 0. If Y1 equals 1, therefore Y2 equal Q bar, or the reverse of Y2, which is, we can say as Y2 star, and we can replace actually Q, or I can rewrite it like this. I'm sorry, I apologize about this. So here is Q star. I'm going to substitute Q as, let me redo it, I'm sorry. Because it's correct, but I'm going to just make the notations clear. So I'm going to substitute Q with Y2, and here is Y2 star equals to J, which is given here as Y1 times Q, which is Y2 bar, plus K1, which is 1 bar, K is 1, and the Q2 is Y2. Then this will be 0, because Y1 bar, 1 bar is 0. Therefore, Y2 bar equals Y1, Y2 bar. Therefore, we can say if Y1 equals 0, then the next Y2 will be 0. If Y1 equals to 1, then the next Y2 will be the opposite of Y2. Just flip it. So in other words, look at the inputs, which is Y1. If Y1 is 0, then you need to make it 0. Y2 will be 0. If Y1 is 1, then just make the complements of the inputs. How? Start here with the initial condition 0. Keep in mind, as I mentioned, it's rising edge. So since rising edge, the update's happening here at the positive edge. At the positive edge. So the updates will happen only whenever there's a green arrow. So let's look here. Here, the first updates will happen only at the arrows. All of the updates will happen only at the green arrows, as we see here. So the first update y2, or here we get the first update, y1 is 0. And we mentioned here, if y1 is 0, then y2 star will be 0. So therefore, it will make it 0, because y1 is 0, until the next updates. The next updates, y1, here is the next update, y1 is 1. Since it is 1, according to the equation, if y1 is 1, then y2 star will be the complements. So we need to do the complement. The complement of 0 will be 1. Wait until the next updates. Here in the next updates, y1 is 1. According to the equation, if y1 is 1, then do the complement. So let's do the complement, which is making it 0. Then until the next updates. So here, the next updates, y1 is 1. So since y1 is 1, then you need to make the complement. So the complements, which will make it 1. Then wait for the next updates. The next update, it is 0. Since it is 0, it will make it 0. The next update, y1 is 1, then do the complements. The next update, y1 is 1, do the complements, then make it 0. Okay? Let's do it again. We started with zeros. The first updates, it's already 0, then it will remain 0. Because if it is y1 0, then it will be 0. The next update here, y1 is 1, then do the updates. Because again, the updates will happen here, 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 and here. These are the location of the updates. So the first update will remain 0. The second update, since y1 is 1, then do the complement, which is 1. The second updates here, y1 is 0. I'm sorry, y1 is still 1. Then it is 1, do the complements. Then the next updates here is y1 is 1. Then keep doing. It will flip. Then here is y1 is 0. It will go to 0. Then the last one here, or before the last one, which is y1 is 1. Then do the flipping or the flip it, or do the complements. Then the last one, which is y1 was 0, which is 1, do the complement as well. Okay? So you need just to be cautious when you draw these ones. Now the last one, keep in mind the input now is y2 and it's falling edge. So the last one, I'm gonna draw it with purple color. So here it's falling edge, and we have the input is y2. So according to the T flip-flop, Q star equals to T Q bar plus T bar Q. Okay, now let's substitute Q as y2, y3. So y3 star equals T, which is y2 times y3 bar plus y2 bar times y3. And keep in mind it's falling edge. Now let's have these scenarios. If y2, or in other words T, equals to 0, this will make y3 star equals to y3. If y2, or in other words T, equal to 1, this will make y3 star equal to y3 bar. So in other words, if it is 0, then keep it as is. If it is 1, then flip it. Keep in mind the updates happening here at the falling edge. So here is falling edge, falling edge, falling edge, falling edge, falling edge, falling edge, and falling edge here. So assume 0 initial condition. The updates happening here. This is falling edge. This is falling edge. Falling edge here. Falling edge here. Falling edge here. Falling edge here. Here. Falling edge here. So whenever there is this line, then we will be falling edge, or at the falling edge there will be an updates. So it will keep 0 until reaching this update. At this update, y2 is 0. Since y2 is 0, there will be no change on y3 because I'm sorry, let me check it. If it is 0, yeah, there will be no change. Then the next update, y2 is 1, then flip it, which will make it 1. The next update here, y2 is 0, keep it. The next update, y2 is 1, then make it the opposite, which will be 0. The next update is 0, didn't do anything, keep it. The next one, it is 1, then flip it, make it 1, or make the opposite. The next one is 0, keep it, and that's it. Okay? So that's all about this timing diagram. I think in the answer sheets or the answers that I provide, maybe it have a different waveform because that one, I think I assumed the input based on X. If the input based on X, it will be different than the waveform that I have in the answers. Yes?
So yeah, it is a little different.
Yes. So, I mean, you need to consider this because in the other one, when I did the first draft there, I assumed X entering here, X entering here. So if you enter X there and there, then it will be different than what we have in the answer notes. Okay? Any question? Okay. Now, before moving to the new topic, you need to make sure how to do the all of this timing diagram using looking at the inputs and the outputs, and do the make sure the first step is to determine the flip-flop type. Is it or is it latch or flip-flop? Is it D flip-flop, D latch, or T flip-flop, etc. All of this. Then you need to know the equations, then do the analysis like what I did here. Then you can apply it to the drawing. Okay? Again, any question? Okay. Let's move, or let's go to another topic, or keep talking about the synchronous sequential logic. So far, we already discussed about the memory elements or the storage elements. So I mentioned that the sequential logic circuit, there must be a storage element. Then after that, during the last 3 classes, I mentioned I was discussing only information about the storage elements, but I didn't discuss how to solve the sequential logic yet. So now, before discussing any sequential logic, we need to know some foundations. So the memory elements, which is latches and flip-flops, has already been discussed. So we know what does latch mean, how can we store data on it, what does flip-flop means, how we can store data on it. Then we realized that the best elements or memory elements is to use flip-flops, not to use latches. Then using flip-flops, we can store the data such that the group of flip-flops can be called as registers. And then the group of registers can be used to create a memory, while the register or the flip-flop is used to store only 1 bit. So if in order to store a byte, you need to have 8 flip-flops, which is called 8 bits register. And if we need to create like more than multiple registers, then we can create it to create our own memory element. So sequential logic circuits, we need to have some analysis and new tool in order to plot a circuit diagram. We need to have some things called state table or state diagram. This is something very important, very essential for our design. So before making our own design, we need to determine something called state table or state diagram, because this will regulate our answers. Then by using this state table, we can create our own function, or we can create our own design using sequential logic circuits. So before going to the design problems, let's learn what does state table mean, how we can create a state table, how can we convert a written problem into a state diagram or something called state table. So what does the state table mean? So it's a graphical representation. It will tell you about the behaviors of sequential logic circuits. So most likely the state table, it will be associated with what shall we do next, depending on the given information. For example, let's assume we have a traffic lights. So we have a state red, then, or a state green. Then this state, the next state, it will be orange. The next state, it will be red. And so on. It's sort of like a circle. It will go as a circle. So therefore, we need to have a state so we can expect what will happen next. So this is something important for us in programming. So basically, the states will be represented by circles. The state transitions will be replaced by arrows. And for example, we will need to move from present state Y to next states, for example, Y bar. Then there are two types of models that can be done. So most likely, the states, for example, here is a state A, or for example, state green. Then I'm going to move to orange, or for example, state B. Then I need to move for red, which is state C. Then move like this. So each state will be inside a circle. Then the action that change the states, it will be as arrow. Okay? The states can be represented into two models. The first model is called Mealy model. The second one is Moore model. So the first one, the arrows has inputs and outputs on the label, while however the other one, the arrows has inputs while the output is mentioned inside the states. This is the only difference between them. Like what? Let's assume, for example, I have state A, here is B, here is C. For Moore's model, for example, I'm going to assume this is input 1, output 0. Here is inputs 0, output 0. Here is, for example, input 1, output 1. That's in like Moore's model. I'm sorry, it's Mealy's model. However, in Moore's model, we can write, this is state A, for example, output 0. Here is state B, outputs 1. State C, outputs 0. Then the arrows will give you some indication for some reason. So you will see by looking at these two state tables, you need to realize, to distinguish what's this model. So the first one, Mealy model, you will see on the arrows inputs and outputs, while in the circles are the states. So here are states, here is inputs, here is outputs. This is in Mealy model. While in Moore's model, here is states, here is outputs, here is inputs. Okay? This is the difference between them. So whenever you look at this diagram, you need to distinguish. This is written in Mealy model or Moore model. Let's go to the first one, which is Mealy model, and see an example with it. Assuming this is the first number 1 model. Here, keep in mind, I'm going to write some information. the output is a function of states and inputs. This is one of the most important things. And here we have arrows have inputs and output label. Okay? So you need to be aware of this. Now, let's assume this scenario. We have the inputs, only one variable inputs, one variable outputs, and we have states y1, y2 like this. So whenever we see 1, 1 and y2 like this, so you can call the states like, we have three states, 0, 0, 0, 1, 1, 0. You can keep them like this, or you can say, I can call this state A, I can call this state B, or I can call this state C, or you can say A1, A2. Yeah, just give it a nickname. Just give each the, so, or you can keep it like 0, 0, 0, 1, 1, 0. It's up to you. So that can be fine. Then here, I'm going to assume them as A, B, C. So let's assume this state table given. I'm going to assume this one is given in the question or in this example. So here it is 1 over 0. Here it is 0 over 0. Here it is 1 over 0. Then here is 0 over 1, and here is 1 over 1. Here is 0 over 0. You need to be aware, look at the arrow directions because these are very important. Now, we have this state table written in Mealy model. Why is it in Mealy model? Because we see the arrows, they have the inputs and the outputs on it. So basically, in order to understand this very well, we need to draw something called state table. So this is called state diagram. Now we need to draw state table for this. So state table, how we can draw it, basically we need to write something like present states. The present states are A, B, C. Then here we will have the inputs, possibilities. We have only one input, so we have 0 and 1. Then we will draw the outputs with each states, the outputs and the states together. So for the first one, locate where is A. Here is A, state A. Now A, if we have the input 1, it will go to C because this is input 1. And the output will be 0, right? Do you agree with me on this? A, the inputs. If we have locates the A. So A, there will be two outputs or two arrows goes out of it. If the input is 1 or if the input is 0. If the input is 1, it will go to C. If the input is 0, it will go to B. And the output here will be 0, the output here will be 1. Okay? So we can write it based on this diagram such that if the input is 0, here is the input is 0, it will go to B and the output will be 1. So we're going to write it like this. If the input is 0, the output will be B, the output is 1. How about if the input is 1? If the input is 1, it will go to this path, which will go to C, and the output is 0. So it will go to C, the output is 0. Yes?
Does the denominator, like 1 on the denominator, mean it's completed?
The one here? No, this means the outputs.
Okay.
So it doesn't mean, it just give you an indication at the output. So again, this is the state. Here is inputs. Here is outputs. So when we draw here the table, we just want to make sure it was out. Yes?
That's going to be very lost in like how to create the diagram. Like how do you know like where to draw the arrows and like what they mean?
Do you mean the original diagram?
Yes.
Yeah.
How did you get the original diagram?
Yeah, I'm assuming this is given.
Oh, you assume it's given?
Yes.
Oh, okay.
So here it's given. Then, here just my target is try to convert the diagram to the table. That's the points. How did I reach the diagram? Let's assume this has already been given. Then we're trying to understand this diagram very well. So let's look at, now we are done with the state A. Is there anything that's going out of state A? We are done. We're done with this one, done with this one. Then let's go to state B. State B, if the input is 0 and if the input is 1. State B, here is state B, here is the input is 0. If the input is 0, it will remain at B and the output will be 0. Therefore, we will write it as B, the output is 0. However, if the input is 1, where it will go?
Here it is B.
Okay. So in B, if the input is 1, it will go to A, and the output will be 1 as well. So if the input is 1, it will go to A, and the output is 1 as well. And that's it. This is the only two possibilities for B. Let's go to C. C, if the input is 0, it will go to A, and the output is 0. So we're going to write it as A over 0. Then the other possibility in C, if the input is 1, it will remain at C and the output is 0, right? Then we will write it as this. C and the output is 0. So now, I think everyone should be aware how to convert state diagram to state table and the vice versa. So if we have state table, how can we do it? Let me do the opposites. I have the state table and I need to make the state diagram. We have 3 states. I can make this is A, this is B, this is C. So the first one, if A, the input is 0, it will go to B. So it will go to B, and I will write 0, the output is 1. Now, the second option, which is C, if the input is 1, it will go to C, and the output is 0. It will go to C, and the output is 0. Now, state B. If the input is 0, it will remain at B, and the output is 0. If the input is 1, it will go to A, and the output is 1. Then C, if the input is 0, it will go to A, and the output is 0. If the input is 1, it will remain at C, and the output is 0. Now, is this one the same as this one? Yes. I mean, here I used A, B, C, but just flip A, and B, and C. Then you will get the same. Okay? So you need to be aware how to convert between these two. State table, state diagram, and state diagram, and state table at the same time. Now, we need to, let's look at this example, timing diagram. with Mealy model. Determine the output response of the following sequential circuits. The input sequence x011010, and let's assume this graph is already given, whereas the value of the sequence are applied to t0 until t5, as we see here, these periods. The circuit begins in state A. Now we will assume the update will happen at falling edge. And the states begin with state A. We will see how the states and the output will be based on the inputs, and assuming the Mealy model that we have here. I'm going to redraw it. Here is A, B, C. Here is A, here is B, here is C. For this Mealy model, A will go to B, 0, 1, then here, 1, then 0/0, then 1/0, then here 0/0, then here 1/0. I'm just assuming this is the state diagram, and we need use the state diagram to make our state table or state diagram here, to draw the timing diagram with it. So initial condition with state A, and the updates happening at the falling edge. So keep in mind that I'm going to write a note here. In Mealy model, the outputs can change between the clocks. Between the clocks or between the edges, which means output can change instantaneously. This is one feature of it. Outputs can change instantaneously. You don't need to wait until the next edge. Why? Because the outputs is a function of both states and inputs. So just keep in mind that the outputs might change during the interval. You don't need to wait until the next updates. The next updates, or we see here the edges are here, like T1, T2, T3 until T5. These updates, which will happen only at the states. But the outputs during the plots or during the waveform will be changed. You need to keep this in mind. So let's assume we have the outputs or the initial condition, state A. The input is 0. Initial condition, state A. The input is 0. What will happen to the outputs? Will be 1, right? Is this right? Because the input is 0, the output will be 1. Therefore, the output here is 1. Even though it's not given in the question, it is 1, but we realize this based on the state table. Okay, do you agree with me? The output is 1 because we are in state A. The input is 0, so the output will be 1. Now, the first update will happen to the states. We have the input is 0, the state A. Where will it go when the state A? It will go to B. Is that right? Input is 0, it will go to B. Therefore, we can say that the next state is B. Now the input is remaining 0. The input here is 0. Now we are with state B. The input is 0. What will happen to the output? 0, right? Therefore, the output will be moving to 0. Because now we are with state B, then it will be 0. Should I say it will remain 0 until the next updates? No, because it's function of inputs. Let's see, the input here in the middle cycle has been changed to 1. So in the past, when it is 0, it will be 0. Now it has been changed to 1. When it's been changed to 1, the output is 1. Therefore, when the output is 1, it will be updated. When the input's here, it will be 1. It will be updated to be 1. Related to the input, because the input is changing to 1, the output will be changed to 1. Now here is the next changing cycle at T1. At the next changing cycle, we already in state B here. So we are in state B. Then in state B, the input is 1. It will go back to A, right? So it will go back to state A. Keep in mind, changing the states happening only at the negative stage, which is at the falling cycle. Or look, we need to wait until the falling cycle for changing the states. But for the outputs, it will be different depending on the inputs. So, because it seems that in the first, like here in the middle, the first selection, it was 0. So it was for the input 0. Then the output is 0. So it was expected the first selection to remain at 0. But during the middle cycle, they change their mind. They change their mind, they make the input is 1. Therefore, the output should be changed. Even though you are in the middle cycle, it's not been updated yet. So if there is any change in mind or any change in the cycle, this will not affect in the state because we haven't updated yet. However, for the outputs, it will be affected because the arrow has been changed from this one to this one. When you change the arrow, you already changed the outputs, right? That's what it had. That's why we have this. Now, again, this cycle, we are in state A. We agree on this state A. Now here, the output is 1. So state A, I'm sorry, the input here is 1. Let's go to state A. The input of state A is 1, so the output will be 0. That's why we need to move back to 0, because at input 1, the output is 0. Input 1, the output is 0. Okay? Now, is there any mid-cycle change? No. Let's wait until, let's go to the next update. Next updates, we are with A. The outputs, the input is 1, output is 0. So the next cycle will go to C, right? So it will go to C. So the next state will be C. Now, with C, the input is 1. Here is C, the input is 1, the output is 0. So the output will remain 0 even though the input is 1. Now, is there any mid-cycle change? Yes, there is a mid-cycle change here. So the input will be 0. When the input will be 0, let's go back to C. Here is C. the input is 0, the output will be 0. So the output will remain 0. So the only thing why the output is remaining 0, even though there is a mid-cycle change, because it's still 0 here. Both arrows, when we switch from 1 over 0 to 0 over 0, it will remain, the output will be 0, remain over 0 in both cases. Therefore, during this mid-cycle updates, the output will remain 0. Then there is no other mid-cycle update. Then at T3, in T3, we are the next update of the states. We are in C, and the input is 0, the output is 0, then it will go directly to A, to state A. So, redraw or write the new update, which is state A here. When writing the state A, the input is 0. We are at state A. The input is 0, so the output will be 1. Therefore, the output will be switched to be 1. The output will be switched to be 1. Okay. So what will happen now? Is there any mid-cycle change? Yes, we have a mid-cycle change here. Let me mark them in different colors so we can know those are mid-cycle changes. The mid-cycle, there is a mid-cycle change here, which will be from 0 to 1. Then look at A. Here is A. Then it will move from 0 to 1. We will use this one. Then it will be used from 0 to 1. Therefore, when it's moving from 0 to 1, the input is 1, the output will be 0. Therefore, the output will be 0 instead of 1. We'll move from 0 to 1. From was 1 in the beginning, the outputs, when the input was 0 to 1, the output was 1, will be 0. So switch the output to be 0. Is there any other mid-cycle updates? No, then it will be 0 and wait until the next updates. For the next update, we are at state A. The input is 1. The output is 0. It will go to state C. So the next state is state C. Now in state C, is there any mids, or in state C locates what will happen to the inputs? In state C, the input is 1. Let's go to state C, which is here. The input is 1. Then if the input is 1, it will remain at C with the output 0. Therefore, the output will be 0. Then look at, is there any mid-cycle updates? Yes, we have here mid-cycle updates. In the middle cycle updates, we will see that the input was 1 with output 0. It will be moving to 0 over 0. So if it is input moving to 0, it will remain no change because it was 0 in the past, now it will 0 in the future. So it will remain zeros. They will remain zeros, so it will be 0. Wait until the next update here. We are with C, and the output is 0 over 0, then which make it goes to A. So the next cycle, or the next state will be A. What will happen to the outputs? If the input is 0, we are with state A and the input is 0, which will make the outputs go to state A. The input is 0, will make the output 1, which will make the output 1. Now, is there any mid-cycle change? No. Then that's it. It will remain like this. So you see, you need to be very careful about it, which is determining the states is much easy. The update's only happening at the falling edge, which is only at the green down arrows, these green arrows. But when you do the outputs, you need to look at any changes happening with the inputs. So if there is any change in the input, this will affect onto the states. If there is any change in the state, or if there is any change in the inputs, this will affect on the outputs. If there is any change on the state, this will affect on the output as well. So you will see the output has been affected into two factors, inputs and states. Even though in this area, the input is fixed, is constant, but you will see some change here. Why? Because there is a change in the states. And the same way, even though here we are in the same state B, but there is a change on the outputs because there is a change on the inputs. Let me present it again. During this cycle, we are with state B. No change on the states. But we will realize there is a change on the outputs. Why? Because there is a change on the inputs. However, in this area, there is no change in the inputs, but there is a change on the outputs. Why? Because there is a change on the states. Because, again, this output will be changed by either changing the states or changing the inputs. You need to keep this in mind. This is in Mealy model. However, in Moore's model, it will be different scenario. Okay, any questions about Mealy model? Yes.
Is it always assumed it's falling edge?
It's depending on the question. So we will. So here in this question, I mentioned it will be in falling edge. So it can be either falling or the rising edge. In case if you don't see any information, is it falling or rising edge, then the default is rising edge. In case if there is no information given. Let's go to Moore's model example. So in Moore's model, we will assume some factors. We can either assume them A, B, C, or I can assume them as W, X, Y. Let me assume W as 0, 0, X as 0, 1, Y as 1, 0. Here in this scenario, I mean, look at, because we know it's 2 bits. 0, 0, 0, 1, 1, 0. What will happen to 1, 1? It's just not used. 1, 1 states is not used. Just keep this in mind. This state is not used. Now, I'm going to assume this is given. This is the plot diagram that I'm going to draw now, or the state diagram. Here is state diagram. Then we need to draw the state table. So here is W over 0, X over 1, Y over 0. And this diagram is different than Mealy model because the output is associated with the states. Then the output is a function of states only. The output is not a function of the inputs. It's only a function of states. So here we can write it here. The scenario, the output is a function of states, not inputs. So only states. Okay? Here, arrows have inputs only, no outputs. While outputs is listed with states. Okay? You will see that each circle has states and inputs, states and outputs. I'm sorry. Here is states. Here is outputs. Now, for the arrows, you will see inputs only. Here is 1. Here is 0. Then here is 0, here is 1, here is 0, here is 1. So those are only the inputs. So in Moore model, you will see only the outputs. I'm sorry, you will see in the arrows, you will see only the inputs. You will not see any outputs at all. So any changing happening in the middle cycle will not affect the outputs. This is the difference between Moore model and Mealy model. When you do the timing table, any mid-cycle change, this will not affect the output at all. And in state diagram, there will be only on the arrows the inputs, while the output will be associated with the states. So in order to draw the state table, so we've already done the state diagram. How about the state table? The state table, here it has the following. Presence, states. Here's inputs, which can be either 0 or 1. Here is outputs. So present states we have W, X, and Y. Now let's look at the state W. When we are at the state W, present state W, the output will be 0, right? So therefore, we will write 0 here. That's it for the outputs. Look at the state X, the output is 1. Then whenever there is a state X, the output will be 1. Look at state Y, the output is 0, right? Therefore, the output is 0. Then now, what will happen to the next states? When we are with W, the inputs, if the input is 0, we will go to Y. If the input is 1, we will go to X. Then let's write it here. If the input is 0, we will go to Y. If the input is 1, we will go to X. Then let's go to state X. In state X, if the input is 0, we will remain at X. If it is 1, we will go to Y. If it is 0, we will remain at X. If it is 1, we will go to Y. Now let's locate Y. Here is Y. If the input is 0, we will go to X. If it is 1, we will go to Y, to W. If it is 0, we will go to X. If it is 1, we will go to W. Then that's it. Okay? How can we make the opposites? Let's assume that we have the state table and we need to draw the state diagram. So basically, here is W, here is X. Okay, let me rewrite it again. W, here is X, here is Y. Now the output is associated with the states, so it will be over 0, over 0, over 0. Then make a circles. Then here. After that, look at the inputs. We are at W. If the input is 0, it will go to Y. If the input is 1, it will go to X. For the X, if the input is 0, it will remain at X. If the input is 1, it will go to Y. Then in Y, if the input is 0, it will back to X. If it is 1, it will go to Y, to W. Okay? Then compare this with this one, they are exactly the same. Any questions? No. Okay. Let's go to the timing diagram using Moore model, Moore example. In Moore example, timing diagram, actually it's much easier than Mealy model. So basically, let's assume the initial state is the state W, which is state W here. Then the updates, let's assume happening at the negative cycle. Now the updates happening only at the negative cycle for both states and the outputs. here updates only at negative cycle or at the edge. Because here the outputs is only function of states. Okay? So any change, any mid change in inputs won't affect the output, will not affect the outputs. Won't affect the outputs, which is different than Mealy model. So, starting with state W here is associated with output 0. Therefore, the output here is 0. Now, the input at this updates, and this updates, the input is 0. If the input is 0 when we are at W, the next bit is to go to Y. So the next bit will be Y, and the output of it is 0. So the next bit is Y, and the output will be 0 as well. You see here there is a mid change, but this will not affect anything, this mid change. So this one will not affect anything. Then here we are with Y 0, and the updates happening here. Updates happening here, which will make it 1. When there is 1, here is Y, and the output was 1, which will make it go to W. So 1 will make it go to W, and W actually, since we are moving it 1 and W, and the output is 0, so the output will be 0 as well. So here is, it will go to W and the output is 0. Don't worry about any change in the middle cycle because the output is only function of states. Whenever there's change in the state, there will be change on the outputs. Now, we are with W, and the input is 0. If the input is 0, it will go to Y. So it will go back. Let's see here. If the input is, I'm sorry, here is the input is 1. Apologize. Y, the input is 1. It will go to X. So here it will go to X, and X is associated with inputs 1. I think, yeah. Is associated with input 1. Therefore, it will, whenever we are with X, it will go to 1. Here is X, here is 1. Even though there is a middle cycle change in the input, but it doesn't matter. It will not affect the output because the output is only function of states. Now, in the next updates, here, we're already done with this update. Next update here, the input is 0. So we are with X, the input is 0, we will remain at X. So there will be no change. And the inputs, or the output, is associated with the X. Even though there is a mid-cycle change, but that's fine. There will be nothing. Now at this updates, the input is 1. We are at X. The input is 1. We will go to Y. And Y, the output of it is 0. So we will go to Y with output 0. The next cycle will be Y, and the output is 0. Again, there is a middle cycle change, but doesn't matter. This will not affect on anything because the output is only a function of states. Now the last one, we are with Y. Here is update. We are with Y, and the input is 0. If the input is 0 and we are with Y, it will back to X. and the output of x is 1. So it will back to x with output 1. That's it. Okay? Is this clear? Any question? Okay. Now I'm gonna tell you about these two tables, just a quick comparison. So overall, for the state table, we have Mealy model and we have Moore model. In Mealy model, it was present states, inputs 0, 1. For example, here is A, B, C. Then, for example, here B over 1, C over 0, B over 0, A over 1, A over 0, C over 0. For example, in Moore model, we discussed so far in that example, present states, inputs 0, 1, and there is outputs. Okay, so it was like W, X, Y. Here is Y, X, X, Y, X, W, 0, 1, 0. That was in two models. That's in the textbook, which is we have Mealy model, its own state table, Moore model, its own state table. However, in these notes, or even like in other textbook, in this textbook, we need to use this one or this one. But in other textbooks, they used another table. It's called generalized state table, which is this generalized state table can include or can be valid for both Mealy model or Moore model. So this is called generalized state table. This is not written in the textbook. So the generalized state table, the advantage of it, this is written in other books, in other references. This can be valid for both Mealy and Moore model. Mealy and Moore model. For both. So we don't need to worry about, when we do it, it can be valid. So how this looks like, this generalized table. We have a present states. We have inputs. We have next states. Then we have outputs. That's how we do it. So let's do this for the example of Mealy model. Let's try to apply Mealy model here. Can we do it? Yes. So basically, we can say this state A, this is state A with input 0, input 1. State B with input 0, input 1. State C with input 0, input 1. Then we can compare with A, input 0, A, input 0, it will go to B, next state will be B, and the output will be 1. A with input 1, next state will be C, the output will be 0. B with input 0, next state will be B with output 0. B with input 1, next state will be A with output 1. C, next state will be A with output 0. When the input is 1, it will be C with output 0. So we will see that these two are the same when you do this model, which is the generalized model. How about trying to apply this in Moore's model? In Moore's model, we have present states, inputs, next states, outputs. it's the same way. So we can, the good part about the generalized model, we don't need to do it for everything. So it's, I mean, we don't need to, it can cover both cases. So here is, we need to convert this here. Here is state A, B, B, C, C. So with input 0, 1, 0, 1, 0, 1. So the next states, when the input is 0, let me make it, I'm sorry, we should assume it W, X, Y, Z. W, W, come on, sorry. W, W, X, X, Y, Y. With W input 0, it will go to, here is W input 0, it will go to Y. With W input 1, it will go to X. And the outputs both are zeros. With X, the input 0, it will go to X. With input 1 will go to Y. The output of both will be Y, 1. With Y, the inputs will be, if it's 0, it will be X. With 1, it will be W. Here is X. Here is W. And the output of them will be zeros. So the overall, you can compare between these two tables. We already converted Moore's model into a small table like this, Mealy model to the small table like this. So this generalized table advantage, it can handle these two with one table. Handle these two tables. We can make the generalized table, then we don't need to worry about the notation. So you need to be aware of all of these three models. And this will be required for all of these three. Most likely in our design analysis problems later, we will focus on the generalized model. But so far, since we are still learning these models, you are required to know all of these three. Again, the advantage of the generalized model, it can cover both Mealy and Moore model. And as we see here. Next lecture, we will go to example, a real some practical examples to see how we can handle, how we can solve this during using Moore's model and Mealy model. How we can draw the state diagram and make the state table. And as we know,